Northwest Natural Resource Group held this socially distanced workshop on San Juan Island in August 2020. In this video, NNRG's Kirk Hanson, San Juan forester Carson Sprenger, and biochar expert Kai Hoffman-Krull will walk you through the ways you can understand your San Juan forest more deeply, improve its resiliency to fire and other natural disturbance, and even create better habitat and a valuable soil amendment in the process.
I'm Carson Sprenger. I grew up on Waldron Island. My parents bought property a little before I was born in '72. So I lived there about 10 years, and then my family went to Bellingham so we could finish school. There's no high school on Waldron. Then I went to Evergreen State College to get my undergrad in natural resource management. Then I got my master's at University of Washington in forest ecology. And pretty much right after I finished school, I started consultancy, Rain Shadow Consulting. And it's been, I think, on its 16th year now. Commercial and residential tree service, non-commercial forestry work, so fuel reduction and thinning, and habitat restoration. So we've done some shoreline restoration work and also Gary Oak restoration, that type of stuff. And I chose this spot in particular because we're on a little bit of a gradient here. So we're standing in that little concavity, like we described, with more available moisture, a little bit different aspect, and kind of right up over this hill as we'll progress through your different stations, we'll come up to a fairly pure Douglas fir stand, thinner soils, more of some exposed rock, and then an aspect which gets more sun, more solar radiation. And the aspect is a big driver of vegetation. Aspect and soil depth are very big drivers. One of the defining features of San Juan Island forest, as I've come to recognize and understand, is we have a great deal of variability across small scales. So that is small scales, you can interpret that as short distances. Lots of topographical variation, you maybe describe it as microtopography. And a great deal of variation in soil depth. So with abundance of rock outcrops and some glacial soils and some very fine textured soils as well. So you kind of combine the topographical variation with the variation in soil, and in general a low rainfall, you get a lot of variation over short distances, a lot of variation in vegetation types. So that is it's just one of the backdrops to when we describe stands. As foresters, we sometimes struggle with defining a large enough stand to kind of fit the description of what a stand is. Well, it's relatively uniform. It has, this age of tree, and it's, they have various degrees of crown health and so forth, because everything is really just quite mixed up. And another theme that adds to that complexity, if we weren't already complex enough, we have our logging history. And the logging history, or landscape history, I'll say the logging history, was really defined by resource extraction, and typically a pretty short, one-time approach to the resource extraction. For a variety of reasons. There was settlers here that came to, really try to eke out some sort of living here. And for a long time, the economics were such that there was not a lot to derive from the land. Relatively low quality soils, the trees were shorter, that they grew slower. We had some benefits for in terms of log transport via the marine, dumping logs in the water, so that sort of could provide some efficiencies. But by and large, the logging history was sort of a short-term extractive based. And the word that oftentimes, or the phrase that oftentimes gets described or used for the style of logging is high grading. So that's sort of it's the poorest way to do selective harvest. So high grading really means like, well, I'm just going to take whatever trees I can get the most money for, take the best quality, and not care about the rest. And they will just be incidentals, And your typical high-grade logging operation was just get the saw timber out that made the most money and move on, and may never get back to that site. So that high-grade harvesting, it does a couple of things. We really didn't have clear cutting here very much. Yeah, I can see some fields were completely cleared and maybe the debris burned. But from a timber harvesting standpoint, very little clear cutting. It was really just selecting the larger trees, and we kind of went through, at least most forests, most stands have at least 2 iterations of high-grade harvesting, sometimes 3, sometimes 4, and they were still implementing that to various degrees through the 90s and even more recently than that. So what you get with the high-grade harvesting is you sort of get a collective loss of vigor and, over time, a loss of stand quality. You're taking sort of the best candidates to occupy the site for the longest amount of time. Sometimes you're taking some of those seed trees out of the picture, and you're creating a different assortment of trees that are going to regenerate and fill in. Oftentimes, the trees that survive are the ones that maybe had their top broken out or bumped against by a log or a cable, and so you get a higher incidence of disease in the stand, and then you get a lower quality tree. We're talking about Douglas firs, and we'll talk about thinning and the response that you can expect from a tree that through thinning gains access to light. When a Douglas fir is very low vigor, that is, it's lost much of its live crown, it will respond to a thinning, that is if you remove the trees around it and give it access to light, but very slowly. When they really get into that low vigor, very reduced crown, it takes many decades for them to rebuild their leaf area, literally their leaf area, their engine that drives photosynthesis and energy. It take a long time. So they're typically not the best candidates to leave. The assumption may be, well, we'll take the big ones and the little ones will just grow up and that'll be the next crop. It's really not the case for Douglas fir so much, especially when you have a tree that has kind of lost a lot of vigor. So your typical stand structure, like I said, is hard sometimes to describe. They're all kind of crunched up and mishmashed together, and then you overlay the high-grade harvesting. And the benefits, I will say, about the high-grade harvesting is there are a lot of remnants from the old growth forest, if you will, or legacy features left over from sort of pre-settlement times. That is the quote ugly or damaged or non-marketable trees, they did just leave behind, right? So they left us, they being the loggers or the landowners. And those are oftentimes great biological hotspots. So those are, they may be partially decayed 400-year-old tree that can support a whole suite of wildlife and it's of a benefit to have those legacy features. Some of those are standing dead trees or just very large, adorned trees with decay and so forth. I would say by and large our forests, they're not simple. There's not a lot of homogeneous, even-aged single species stands here. It's hard to find those. And I think that is, in some ways that's a good thing. So we kind of, our beginning point, which we approach most stands, most lands, is with a fair amount of diversity, a fair amount of structural diversity, and a fair amount of relatively high species diversity. One thing that I always find interesting to remind myself and to talk about is that, and people ask me this, like with the land development and the logging sometimes I see taking place, aren't there far fewer trees now than there were, say, 150 years ago? Should we be replanting trees? They're worried about not having enough trees. Well, it's actually not the case. We have far more trees growing throughout the San Juans in general than we did 150 years ago. And even when you account for the agricultural clearing and the little towns and the developments. Yes, the trees were bigger and they were more widely spaced, but we had fewer of them. And nobody went out and actually counted all those trees, but we have reasonable records from fairly detailed descriptions of the forest, some actual maps, some early aerial photos. We have kind of our understanding of the trends of vegetation and so forth. But one of the biggest pieces of this story, the most important piece of the story, is up till about 150, 120 years ago, that sort of period of active settlement, call it active European American settlement in the islands, which is somewhere around 1860 to 1900, depending on which island you're on, all right? Up until that point, we had very frequent fire. So there was fire across almost all of these low elevation sites. I'm probably going to exclude Mount Constitution and maybe some of these higher north aspects on San Juan too. I guess that'd be Mount Dallas, and what's the other one? Mount Dallas, the tallest? Yeah. Say again? Grant. Okay, Grant. Okay, yeah. So probably those may depart a little bit. Katy Mountain, yeah. So we had fire as a dominant landscape feature that burned across most of these low elevation sites fairly frequently. And how do we know this? Well, we've done tree ring studies using increment cores and chainsaws and log sections. And we've gone back and we've looked at those tree rings and we've found those fire scars, and we've built maps. In fact, there's I could probably name 5 different research projects in the San Juans that have looked at the fire history and characterized the historical, characterized fire as historical events from an ecological perspective. And you may also be wondering at this point, well, if we had so many fires then, how come we don't have them now? And the piece there is that most of those fires were human ignited, human initiated. So Native Americans, the Coast Salish people who were here seasonally and probably year-round in abundance, had a land management tool, that being fire and other aspects, for a period, depending on which island you are, and we're speaking a little bit generally in this, what we know from the ethnographic record and the ecological record, about 2,000 years of managing this place via fire. So intentionally lighting things on fire. And from study sites on Waldron, which I was involved in, Stewart Island, south end of Lopez, a little bit of work on Orcas, Henry Island, Kellett Bluffs, we kind of pieced together the history, literally, from the tree rings. And we talk about fire, we characterize it in terms of a return interval or frequency. How frequent does it come back on average? That can kind of help us understand, what fire likely did and its influence on the landscape. Well, around here on average, from what we know from the tree ring record, it was maybe 7 to 15 years, every 7 to 15 years on average, a fire came through and burned on a particular site. So what we also know is that, maybe every site burned every 7 to 10 years or so, but other sites were burning. So there was probably a fire every year somewhere. What we also know from the tree ring record is we probably didn't capture all of those fire events, so it's probably an underestimate. And when you're in the vegetation type that we describe as more open savanna or grasslands, of which we had in abundance, the fires may have just burned every year on those sites. And the Native Americans had a variety of reasons for burning, some of which we may never fully understand, which we've tried and we've pieced together through ethnographic means. But there were promoting food and promoting hunting grounds, promoting landscape. Some of it was defensive, whole variety of reasons. But when I think about the fact that we had fires, repeated fires, fairly frequently on this landscape, up till 150 years ago, some sites maybe only about 100 years ago we had those frequent fires. The more frequent you have fire, the less fuel builds up, because when it comes through, it burns the woody material and it consumes that. And if it comes back 10 years later, it hasn't been that long for those shrubs to develop and those branches to be cast or that tree to fall over. There's just not a lot of fuel, right? So the more frequent you have a fire, the lower your fuel amount is. And so the lower your fuel amount is, the lower intensity of your fire. Literally, the flames are not that tall. They don't cause that much damage to a tree or the cambium layer of a tree. So you develop a suite of vegetation with that repeated low intensity fire that tolerates that. Douglas fir, oak, and cedar to a certain extent they tolerate fire fairly well. Well, the lifespan of a red cedar right there, or an old growth Douglas fir, I think around here I've aged a Douglas fir at just under 500 years, 480. Some of the cedars may approach that. So fire has only been absent from the landscape for less than half of an age of a fully mature Douglas fir. So if you think about the time that forests may develop over time and mature, that we're really in a pretty young new period, a new regime of forest development. Our forests are really still responding to that cessation of those burning practices.
All right, well, we'll get started. So, I'm Kirk Hanson, and I'm the Director of Forestry for the Northwest Natural Resource Group, and one of the catalyzers for this workshop series, so thank you for joining us. At this station, we're going to talk about forest management, how to assess your forest and how to make some decisions as to whether or not to manage, and then get into some specifics on how to manage if you choose to make that decision. Carson gave you some great context at his site talking about the forest ecology of San Juan forests and giving you some kind of observation skills of how to look at a forest, what's going on, what's led to the kind of current forest conditions. So I want to build a little bit off of that and kind of fine-tune your perspective as you begin looking at this forest, and hopefully give you some tools that you can take back to your own forest to begin assessing its condition and answering that question, should I manage? Why should I manage? And again, that'll lead towards what are some management options. I think to in general answer the question of, should I manage? That's going to be the confluence of two things. One is a very thorough assessment of your forest and understanding what's going on with your forest, in particular in relation to historic conditions, but also relative to, where is my forest going to go in the future if I do nothing? Because a lot of forest management really is about sending your forest on a very specific trajectory, a silvicultural trajectory. That trajectory then is going to be based on what your objectives are. Our organization, the Northwest Natural Resource Group, works primarily with forest owners that are interested in taking a conservation-based approach to forest management. We refer to it as ecological forestry, because what we're trying to do is emulate natural forest processes, but through an active management approach. Now, we work with people that are both managing for commercial timber production, and we also work with folks who come to us and say, I want to put my forest on a trajectory to achieve old growth conditions. I think the sweet spot where we really excel is right in the middle of those two. And it's my argument, and it's what our organization is striving to do, is to say, you can manage both for high conservation values and for sustained timber production. So depending where you're at on that spectrum, the kind of range of assessment tools I'm going to give you in the next couple of minutes, and then some of the management recommendations I'm going to provide, should be able to help you manage, wherever you are in that value or objective spectrum. And I'm a small woodland owner. I manage about 200 acres of forest land, and I'm striving to both optimize the conservation qualities, what we often refer to as the ecosystem services of that land, and produce a commercial crop of timber at the same time. To put a little bit of a caveat on that, all forest management is about compromises. So, we can create a chart of different objectives, and in one corner we can put just pure conservation objectives: wildlife habitat, carbon sequestration, clean water, clean air, etc. On the opposite end of that spectrum, we can put maximizing timber production. Anytime that you're making a management decision, you're likely going to compromise, some of the value somewhere in that spectrum. And so that's just really a question that you have to ask yourself. You know, again, what are my objectives? I feel, again, you can balance a lot of those objectives, but to be perfectly honest, you cannot maximize timber production and wildlife habitat. You cannot maximize carbon sequestration and timber production. You can't maximize clean air and wildlife habitat. All of these different variables at some point in that management spectrum are going to come into some degree of conflict with each other. So what I often talk about is, you know, trying to sort of optimize across that spectrum, again, depending on what your objectives are. So I think a key part of teaching these different forestry concepts and management strategies is more to help folks understand the spectrum of options and how to think about approaching a forest more than literally how to do something. And that way you can take that thought process, that kind of evaluation process, and apply it to any stand that you come to, whether it's this forest, Moran State Park, a forest at your house, you know, wherever, and apply a thought process of evaluating the forest, evaluating your own objectives, and then coming up with management options. If I were to give you some very strict rules of management, thinning to a particular density, maintaining specific tree species, and if you took all of that literally, those literal concepts may not apply in every situation. So what I'm hoping to do with this presentation is give you some tools again for evaluating your forest that you can then go back and see what fits. And not everything I say is going to fit, but you'll have a suite of tools to be able to draw from. So what I want to start out with is an assessment of this forest. And I want to turn this back to you. So recalling where you were at with Carson and the condition, the qualities, the composition of that forest, what's different here? Just objective observation, or subjective in this case. Mossy? A little mossier?
It's drier. Trees are different.
Drier, trees are different. Trees seem younger. Different species. No big trees, comparatively speaking. Now, as I look around, the only species that I see up here are Douglas fir and Pacific madrone, whereas down below, gosh, there was 6 or 8 different species, including a wider range of hardwoods. So there's one other key difference to this stand than where you were before. Okay. What else is really different here? That's different too. More sunlight. The number of trees. Think about the stocking density down there. How many trees there were in that area compared to where you are right now. So when I was down there and Carson was talking, I measured the number of trees within a 1/5 acre plot where I was standing. It's about 52.7 feet in radius. And within that 1/5 acre plot, I measured, I think it was 8 trees. So 8 times 5. If you extrapolate that plot out to the acre, there were 45 trees per acre in that plot. Now what you can see here, what I've set up, we did this yesterday, is a 20th acre plot. Where these 2 ribbons are, this is the plot center, the middle of the plot. And when you look at the pink ribbons that are out in the periphery, there's 4 of them, that defines the perimeter of a 20th acre plot. Within this plot, if we count all of the trees, including the real small diameter trees and the larger trees, there are, and extrapolate this out to the acre, there are 420 trees per acre up on this site, in contrast to 45 trees per acre. So there's 10 times as many trees on this site than there were down there. Now, what are some of the implications on a dry site having 10 times the number of trees than the number of trees on a wetter site? What's a possible consequence or implication of that? Exactly, more competition. And competition for what in particular? What limiting resource? Definitely, and one more. Water.
absolutely. So think about all of these trees as drinking straws in the ground. And as these trees transpire moisture, they're pulling that moisture out of the ground. Now, one thing that we know about soils in the San Juans, they're dry to begin with. And especially as we get to this point in the season, August, start moving into September, soils get drier just by their nature, but also when you have a highly overstocked stand like this, these soils are going to get even drier. And soil moisture becomes a greater limiting factor than sunlight in how these trees are able to grow. So that's just an observation. I'm not going to place any values on that quite yet, but there are a lot more trees here than there even were historically. So take a look now around at the stumps. You're leaning against a big stump there, and look around and see if you can identify other large stumps. Whenever I work in a forest, this is one of the things that I try to do, if they're evident, is look at what the original stocking density was of this forest. In this dry ecology, these big stumps here are the remnants of the original old growth forest. So when I measured them yesterday, there was the equivalent, again, of about 50 trees per acre. So if we can assume that the historic forest condition, 50 trees per acre, was the natural carrying capacity of this site, then what does that tell us about the current stand condition when there's 400 trees per acre? That may be a conclusion that we come to. A lot of die-off, a lot of competition. So you're absolutely right, competition for sunlight. Let's shift to that. When you look up into the forest canopy, the crown is the portion of the tree that has live green needles. And we often use a term and a metric called live crown ratio. So that's the amount of total tree height that is in live green needles. And one thing that you'll find, and this is an indicator of interspecies competition, is that when you look at a small diameter tree and then follow that up and look at the live crown, or the ratio of that tree in live crown, kind of fix that in your mind looking at this one. Now look out and find a larger diameter tree and look up at its live crown ratio. And what's the difference that you see?
There's more crown.
More crown on the bigger trees. So live crown and diameter are directly proportional. The live crown of the tree is the growth engine of that tree. And it makes sense. All those needles essentially are solar panels that are producing energy for that tree, allowing that tree to fix sugars, carbohydrates, carbon within the body of the tree. So the more solar panels, the more needle surface area, the more capacity that tree has to grow and put on wood volume. Just the opposite being true. The smaller the crown, less capacity to grow. So this stand is going into a self-thinning phase. We sometimes refer to it as a stem exclusion phase, in particular with trees that are very moderately shade tolerant. Carson mentioned that Douglas fir tends to lose its lower branches. As it goes into this competitive phase, one of the first things that the subordinate trees lose is that live crown. They're getting suppressed in the canopy, they're beginning to get shaded out, and over time they're going to die off. So we can certainly let nature run its course. This forest will thin itself out. That's perfectly fine. Given enough time, the dominant trees will succeed. These trees will succumb to suppression-based mortality. They'll die off. For a period of time, they'll be standing snags, standing dead trees. Over time, some of them may fall, contribute organic matter to the forest floor. And so we have to ask ourselves a question then, do we want to let nature run its course, or do we want to have an intervention in this forest? And that again gets back to your goals and objectives, your values, and maybe even a broader landscape and societal goals and objectives. What's an implication of not thinning this forest if a lot of these trees are going to die and be either standing dead or down dead? So if fire were to get in here You've got a lot of flammable understory brush. You have a lot of limbs in here. Increasingly, we're going to have more dead trees, like these two little ones back behind us, the madrone. If fire were to get in here, that could be absolutely catastrophic. And I think fire is going to be the single most catalyzing factor for folks to actively manage their forest, to say, I'm going to move from a passive management phase to an active management phase. I want to reduce the risk of fire. Now, you may have other objectives, might be timber production, depends on how many acres you have, depends on what kind of timber economy you live in. Don't live in the best timber economy here in the San Juans. It's hard to sell logs. It's expensive to log. So I think the majority of objectives that folks are going to have here are going to be more conservation-based and fire prevention-based. So with those kind of basic assessments of the stand, we, I think, should be coming to the conclusion, and I would encourage you to come to the conclusion, that you probably want to take an active management approach and do some thinning. The single most valuable tool in your silvicultural toolkit is thinning. It's cutting some trees down, removing some of those straws that are in the soil, reducing competition for sunlight, and in particular soil moisture, and trying to favor the more dominant trees that are already doing better, making sure that they stay as healthy and as resilient as possible and can grow up to be larger, fire-resistant trees that also have a higher timber value, that also arguably provide a higher wildlife value, that are capable of sequestering and storing carbon for a longer period of time. And now you can see how we're starting to optimize a wide range now of different objectives, different ecosystem services, different values within the forest through thinning. So hopefully I've convinced you to thin. Now the question becomes, okay, Kirk has convinced us to thin. I don't want to thin the wrong way. I don't want to take out the wrong trees. So what trees are we going to choose to take out and what trees are we going to keep? If we're following an entirely an ecological pathway, I already gave you the answer of which trees to take out. Which trees is Mother Nature already beginning to weed out of this forest? Small diameter? Not necessarily age-related, but can be. So smaller diameter and exactly the small, the low live crown ratio. Yep. The likely losers. Yep. Exactly. Yep. So all we're doing is following the natural process of self-thinning, but speeding that up. Significantly speeding that up. It could take decades for this forest to thin itself out and get down to that lower stocking density. Imagine going from 400 trees down to 45 trees per acre. It's going to take quite a bit of time. So as you look around in this 20th acre plot, you'll see trees that have orange flagging on them. These are the trees that I've marked for removal. And you'll right away see a rationale to that. I just described what that rationale is. They, by and large, are the smallest diameter trees. I've got one exception back there. There's one that's a little bit larger diameter. But here's what I'm trying to do. In this, we use a term called thinning from below. This is completely the inverse from high grading. Carson mentioned the term high grading, where you come in, you take the most valuable, the biggest, the most dominant trees. That's where you're going to get most of the value out of a stand. We're flipping that completely over and we're thinning from below. Thinning from below means we're taking out trees that are below the dominant canopy. They're the subordinate trees, the suppressed trees. We're kind of culling the weak and the lame out of the herd. So by and large, we're going to take those trees out in our first thinning pass. That's going to be one of our first decision-making criteria. Okay, let's take the trees that are already getting shaded out. After that, we want to think about spacing, getting the remaining trees spaced out a little bit more so they have more access to soil moisture. But also, as we look up, we want to look at the placement of the crown of those trees within the canopy. And to make sure that those trees can continue to grow, we want to make sure the individual crown of that tree has ample room in the canopy to maintain a large, broad crown. So when you look back in there, where there's kind of a high density What I've done is selected one tree right in the middle to pull that out, and there's also a smaller diameter tree in back to take that dense cluster of trees and kind of spread them out a little bit more, get a good spacing on them. So there's two criteria now for thinning. Taking out the trees that are already getting shaded out and beginning to space trees out a little bit more to reduce stocking density. I want to give you a few other criteria as well. So there's another species in this stand, the madrone, and a lot of people love the madrone. I do. It's a beautiful tree. It's part of the biodiversity matrix, provides wildlife forage. Great timber quality to it if you can get it up to enough size. It's a beautiful wood. But as Carson mentioned, madrone is highly stressed right now. We've removed fire from the ecosystem, which is allowing a pathogen to begin infecting the trees. And as you'll also see, Douglas fir grows faster and is very competitive with the madrone. If you look at the crown placement or the canopy placement of the crown of that madrone in the canopy, you can see that it doesn't really have much room, and there's not much crown to that madrone. You've probably seen open-grown madrone. They look like giant oaks, huge crowns to them. When madrone grows in competition with Douglas fir like this, just like it's doing now, it grows skinny and tall. It's reaching for the light. It's a very plastic tree. You often see them bending where that crown finally does occur. It's occupying a tiny little gap in the forest canopy. So if we want to retain madrone for whatever value you assign to it, we need to thin around that to release it, to give it some space in the canopy so its crown can open up or it can retain its crown. So that may be another reason that I'll select some trees in here, is to try to give the crown of that madrone a little more space to grow. So those are a variety of different criteria for thinning. Now, another key thing to keep in mind though is we don't want to come into a stand that has this high of stocking density and over thin. You don't want to take out too many trees, because as you can imagine right now, all these trees are accustomed to growing together. And as the wind blows, they're all kind of leaning on each other. And if we were to come in here and take out too many trees, and a big northeasterly comes along, you could have a catastrophic blowdown. So one of the rules of thumb on a first entry thinning like this, the stand hasn't been thinned in the past, one of the rules of thumb is you never want to take out more than 40 to 50% of the individual trees in here. And of those trees that you're taking out, of that 40 or 50%, they should be the understory trees, the suppressed trees. So by and large, again, you're leaving the most dominant trees, with a few exceptions. Like I just said back there, where you've got a dense cluster, you may take out one or two. So as you look around in here, you're leaning against a very tiny understory tree, and you'll see a few more. There's one right back there that occupies a mid-space in the canopy that I've left. So even though it's small diameter, I've left that one. So I'm going to tell you a little bit about that. And this is about now maintaining complex forest structure. If we were to solely thin from below and just take out the understory trees, we would really push this stand to a very homogeneous condition. All you would have is dominant trees in the canopy and nothing in the understory. That's just like a tree farm. And we don't want to do that. We want to maintain complex forest canopy, trees that occupy various strata in the forest for a few different reasons. And you mentioned a great one, that especially if we're managing for timber production, you want to have that next generation of trees ready to grow up. So when you do eventually do some overstory thinning, take out a dominant tree here or there for timber, you've got something that can replace it. The other thing that we know from a purely ecological biodiversity and wildlife habitat standpoint is that a whole range of insect varieties occupy different strata in the forest. They will forage on trees that occupy different horizontal layers in the forest. So if we want to continue to provide habitat for a broad range of insect species, we want to maintain canopy complexity. Another reason for maintaining insect diversity is we know that different bird species forage on different insect species. So by maintaining complex canopy structure, we provide habitat for diversity of insects. We then provide forage for a broad diversity of bird species. Yeah, so the question is there a way to maintain some kind of intergenerational transfer of knowledge, of wisdom, of management goals and objectives? Absolutely. I mean, the best way, I think, to do that is to develop a written forest management plan that describes the forest conditions at that time, because that becomes a legacy document that future generations can understand, where that forest came from, what some of the management decisions were, but also codifies a certain range of values. We want to manage for migratory birds. We want to manage for carbon sequestration. We want to manage for sustained timber production. So at a minimum, the forest can pay for its own ownership and management costs, if not provide a dividend back to the heirs, the property owner. We want to manage for X, Y, and Z. All of that rationale is explained. So what I find in particular is that it's often the older generation that have come out of an agronomic background that understand managing the land. They understand farming. They understand forestry. And it's the new generations, the younger generations, that haven't been raised in that same context. But if they're given a manual that describes what's going on in the forest, it gives them something they can read, and we can rekindle that understanding of the forest and how it should be managed to meet these different objectives. So that's one of the main things that NNRG does, is help forest owners write complex forest management plans that articulates their goals and objectives, thoroughly evaluates their forest conditions, and then lays out a pathway of management recommendations to match those goals and objectives with the resource at hand. So I think that's one of the best tools. So I think that's it for this site here. I want to move. What we did here is we set up two different plots. This plot represents the before condition, the pre-thinning condition. What we did yesterday is we thinned out another 20th acre plot over there, and I want to show you what that looks like, and then get to the question of, well, what do we do with all this stuff once we've cut it down so we don't exacerbate fire risk? So in this plot, this had almost the same stocking density as the prior plot, a little bit lower, but fairly close. I think this was running about 360 trees per acre, whereas that plot was running 420 trees per acre. And what we did is we thinned this out based on the same criteria that I just mentioned. By and large, we took out the suppressed trees that had small live crowns. We only took out one or two intermediate or dominant trees. And I want to clarify some terms here. We oftentimes classify trees based on their position in the canopy. So I mentioned the term dominant. It's kind of self-explanatory. It's the big tree that's got the crown high up at the canopy. You look behind you at that large diameter tree. Look at its ginormous crown. Clearly a dominant tree. This tree right back here, a little bit smaller diameter, a little bit smaller crown. We would classify that as an intermediate tree. A co-dominant tree. The tree right behind you here, we would classify as an intermediate tree, a little bit smaller diameter, a little bit smaller crown, and then the fourth classification being suppressed tree. So dominant, co-dominant, intermediate, and suppressed. So if one of our objectives, again, is to maintain complex forest composition, that's more representative of what we consider old growth forest to be, we want to maintain trees across all of those different canopy strata, or those different kind of height classes. And what you'll see what we did here with this thinning, we did exactly that. So we've retained that big dominant tree, the dominant tree here. We've retained some of the co-dominants, some of the intermediates, and then some of the suppressed trees that are low down in the canopy. So that was one of the objectives to thinning here, is to maintain complex forest structure. The other thing you'll see now, when you look at the individual trees, they're all nicely spaced out. They've got a fair bit of room from each other, and that's meant, again, to reduce moisture competition. Not all of the trees that are retained, not all of the intermediate or suppressed trees are going to grow up to be future timber, but that wasn't entirely the objective here. Again, part of the objective was to maintain wildlife habitat value. Where we're likely to get the next generation of timber coming out here is more in the co-dominant and some of the intermediate trees. the trees that have maintained the largest life crown have the best capacity to rebuild that crown and get back into a good growth phase once they've been released, once they have been given more position in the canopy to grow up. So it is possible that even some of these trees that qualify as suppressed, that have good crowns to them, now that they have sunlight to them, will start putting on more needles, more branches, and very slowly over time recover. And it's quite possible that they will grow up eventually to be larger dominant trees in the future. So back to your question, okay, we do all this thinning, we put all of this woody biomass on the ground. Didn't we just now exacerbate fire risk? I mean, look around here, and not really. So there's a couple of things that I like about thinning in the San Juans and thinning in dense stands like this. Again, when you look up at the crowns of the intermediate and the suppressed trees, there's not a lot of crown there. There's not a lot of branches. So when I cut that tree down, most of that tree is just the stem. There really isn't a lot of slash that comes from it, which is fantastic. Because like Carson said, it's the fine material, the small diameter material, that is the highest fire risk. So you are going to generate some slash. One of the easiest things to do with it is what I call lop and scatter. Just spread it out. And another general rule of thumb, as long as that slash mat is no higher off the ground, no thicker than knee height, and is not contiguous, a little bit over here, a little bit over there, you've really reduced fire. So that's one thing you can do with it, disperse it. You can also chip it, certainly, if you have those means and the capacity. The other thing you can do with it is you can aggregate it into a tight area. And this is somewhat what I've represented here. One of the other missing habitat features in second growth forests, two missing habitat features, are large diameter standing dead trees, snags, and large down logs. Both of those dead wood structures are incredibly important for wildlife. The standing dead trees, the larger diameter ones, provide cavities for cavity-dependent birds, pileated woodpecker for instance, as well as small mammals. And it takes a tree at least 12 inches in diameter to begin providing kind of optimal wildlife habitat. And usually the bigger the better. The wider diameter, the bigger diameter, the better. Same thing with down logs. For a down log to be sort of optimally functional for wildlife, at least it's going to be about 20 inches in diameter and 20 inches long. So one thing you can do with your cut material is create a constructed habitat log. And that's what we've done here. We've taken the poles, stacked them together into a log that's roughly 20 inches in diameter, 15 to 20 feet long. And there is some architectural significance to this habitat log. It's not just willy-nilly. When you look down in there, you'll see all sorts of little gaps and spaces. That provides some space where small mammals can get in there, salamanders can get in there, amphibians, what have you. And then I took some of the slash, some of the ocean spray, some of the tree branches, and piled it on top. And this can provide some cover for small birds to get in and occupy that if they don't have that type of structure elsewhere in the stand. Again, a nice way to aggregate some of that material. You can certainly disperse the logs all over the place. Studies have shown that in undisturbed forests, and this is true both surprisingly on the east and the west side of the Cascades, there are upwards of anywhere from 50 to 140 down logs per acre. So I don't know when the last time was you hiked through any intact old growth stands, but there's dead wood all over the place. The only way you can get through there is on a hiking trail where they're actively maintained. So again, those types of features are missing here, and I would argue that in your thin, shallow San Juan soils, these soils are hungry for biomass. So by thinning up this forest and accelerating that process of getting wood on the ground and getting biomass on the ground, you're helping to feed the soil. So with the rest of this material, after making some missing habitat structures, I've basically just scattered it. And you can see there's an aggregation of slash over there, but then no slash here, no slash there, no slash there. So again, that's key to not allow that slash mat to be contiguous. The next stop after mine is Kai, and he's going to talk about biochar. And that's obviously something else you can do with the slash. If you have an excess amount of slash, or you want to get creative with it, you can convert it in a very controlled burn situation to create biochar. Carson sort of touched on this, But another ecological phenomenon that we have eliminated from this landscape for a considerable amount of time is the replenishment of charcoal in the soil. Without that repeated burning, we are not adding ash and we are not adding charcoal. And as Kai will illuminate, charcoal is incredibly important for moisture retention and nutrient retention in these soils. So like Carson said also, these forests now are evolving into a very different set of circumstances, very anthropocentrically controlled circumstances that they never experienced before. And one of those key variables that's missing, and this was really an aha to me when I started working with Kai, is charcoal. Who would have thought that charcoal was so essential to these forests? So converting some of this material into charcoal, and you can do it in the woods. Kai's going to show you how you can get that charcoal back out there, and to a certain degree, as best we can, replicate that fire disturbance regime. We're replicating it through active thinning, because fire would have killed out some of these smaller diameter trees, and we can replicate it by converting some of that material to charcoal. Great question. What time of year to thin? I'll just say that there's one time of year that you really don't want to thin, and that is spring, from about March 15th through the end of June, for two reasons. One, that is the prime bird nesting season. So if you're concerned about migratory birds and their habitat, I am, you really don't want to be in the woods with noisy equipment and dropping trees and disturbing their ability to nest. The second thing is, when the sap is rising on trees, if you're out there thinning and you're dropping trees and they're banging against the trees that you want to keep standing, that bark is very sensitive and you can skin the bark off your residual trees, and that can create points of infection for fungi, and just lead to defect to those trees. So I would avoid that time of year. My favorite time to thin is winter time. It's cooler, easier to work. Right now it's wasp season, and enough said.
Well, hi. Yeah, I'm Kai, and I currently work for the Conservation District, basically doing their forest programming throughout the county. And for the last four years more in concentration, I've been working on biochar research in this county, originally with University of Washington, and then with the University of Montana, WSU, and then now with Oregon State University. So it's been sort of this multi-university research project. And we're going to get to have like a little bit of a hands-on Lincoln log project of putting together a conservation burn pile, which will be fun to do a little bit. But before we get into that, I'd like to give a little bit of a larger context around the forest carbon cycle and sort of why we're really asking this question in the first place. Which is, as you know, I'm sure many of the speakers have been saying, these landscapes were fire-adapted landscapes for time immemorial, both anthropogenic fire as well as natural fire. And since fire suppression has occurred, we obviously have had this limit of basically no fire occurring for the past 150 years. And that's had a lot of consequences. You've probably been hearing about the congestion issues that we're having in our forests. But one of the other major issues is what that does for soil and soil health. Ash content has high calcium and magnesium, as well as other trace minerals. But old growth fires produce extremely large volumes of charcoal. 4 to 6% of old growth fires on average produced charcoal. Of the biomass was converted into charcoal. And that charcoal did a whole series of different soil health properties. It has significant water retention properties, roughly 6 times its weight in water in terms of water holding capacity. It has nutrient retention, so it's keeping both macro and trace minerals at the surface layer rather than draining away, which especially in our high rainfall area is really important. And then it has high biological activity enhancements, both that's from some of the labile carbon that's left in the charcoal, as well as the structure of charcoal has, they say, 1 tablespoon has as much square footage as a football field. Basically, it's just full of all these little micropores, and those pores get lodged up with organic matter, and then basically become this feeding ground for microorganisms. So you get this sort of high concentration of microbial activity at the surface edge of charcoal. So, and what research has shown us is that you get a really high amount of benefit for basically 100 years with charcoal, and it basically gets kickstart or restarted every time a fire moves through. So a lot of especially the nutrient and the biological properties get reset and in essence kind of start over. And so really we're at this interesting time frame where fire suppression we're just a little over 100 years from it being national policy. And so we're really only coming into this new time period where charcoal's no longer really having a significant impact in our forest soils. So one of the issues of how we can potentially increase that soil resilience and then the tree resilience, especially within a changing climate, that we're going to be seeing greater stress of drought conditions, higher concentrations of moisture when it's less ideal, like high concentrations in the springtime, so that roots aren't able to access oxygen. Those stressors, and as well as just like heat and cold variations when trees are not associated to those heat and cold patterns, or they're associated to historic heat and cold patterns, and then as those changes occur with climate change, they're going to be under greater stress because they're not adapted to those. So how do we create a more resilient landscape for these trees to be able to thrive? And charcoal is being considered as one of those solutions. Maybe the other simple way to put it is, when you talk about how much congestion we have in our woods and how much material really needs to come out, we are in many ways mimicking the role of forest fires, but we're doing it manually because we don't want to be, in essence, burning our houses down. So then what do you do with all that biomass? And there's sort of a whole spectrum of that opportunity, right? And we're going to be looking at a very small scale option for in-forest produced biochar here, but then there's also the larger scale option that we were talking about with these microgrid bioenergy facilities that we really hope can be on all three of the major islands and potentially run a significant amount of the power within each of the major town centers. And then biochar would just be a byproduct of those, which also I think is an exciting way to potentially get the price point down to an affordable level that farmers could really be able to buy it. That's a whole other conversation in terms of its application in ag. But fundamentally, we're going to be talking about forests, so that's what I'll stay focused on. Yeah, so raw material has a half-life, raw wood material has a half-life of 7 years, carbon half-life of 7 years. That's graded for Pacific Northwest. We probably are a little bit on the upper side of that, being more in the rain shadow here and a little less moisture. So you're probably at more like a 10-year half-life. But charcoal has a half-life of anywhere between 350 to 2,000 years half-life. So it's basically decomposing. Microbes are starting to eat it. They're processing the labile carbon, and then they're dying off. They're going into the soil, and then it's the respiration from the soils then going back into the air. Charcoal basically forms these extremely long carbon-carbon chains, which is why it's considered so recalcitrant and so stable. And it actually has very little of the carbon that microbes can actually process in and of itself. But I was talking about all those micro pockets. They serve as holding ground for all that organic matter to basically get lodged and stored. So in many ways, it's important to think about it as central to storing carbon that microbes can eat, but it in and of itself has a very small amount of labile carbon or bioactive carbon. So as we think about carbon cycles, charcoal is one of those larger pieces to be talking about in terms of forest carbon. And we happen to live in one of the great forest carbon areas. Pacific Northwest stores on average 93 tons of carbon per acre. And we're probably a little bit on the lower side. Our productivity is not quite as high as much as the Pacific Northwest, but we are still in this sort of the highest concentration of carbon per acre really of the United States, in many ways a lot of the world. Pacific Northwest, our climate is only second to the Amazon in terms of carbon storage rate. So we're really in like one of the major areas. And within that, forests globally absorb 1/3 of the carbon that we emit as a human race annually. So it's kind of a number that many of us don't really think about. It's one of the most central ways that we globally process carbon. And when we have these forest fires that come through, you're getting sort of this two edges, or the sword cuts two ways. It cuts one in terms of a major amount of off-gassing of carbon. So 2 years ago, California emitted 15% of their total carbon emissions were from forest fires. And so, just huge amounts going up in smoke, literally, all at once. But then also, you're losing that forest capacity to be absorbing carbon, right? If forests are one of the most central ways that we're absorbing carbon, suddenly the regrowth of these catastrophic fires, which are very different. I was explaining those old growth fires where fires are kind of slowly trickling through the understory. They're taking down some of the smaller trees. They're eating some of the understory, the brush, and then they're scorching and scarring. You've all probably seen those burn scars on the outside of old growth trees. They're leaving the old growth trees fundamentally intact. Those fires, again, are so different than these catastrophic crown fires that we're experiencing right now, that are basically just obliterating so much of the forest. Pretty much all of it is removed, and so then, not only are you kind of starting from scratch, you're also basically burning off all of the organic matter levels in the topsoil. So then it's such a long process to be able to develop and build up that carbon again in the soil to then be able to even build healthy and resilient plants. So I think that people think about fires as sort of a natural phenomenon, but I think we really need to be thinking about these modern fires as not natural at all. They're the byproduct of exactly the issues that you've been hearing about, of the congestion that we've created through our history of fire suppression and commercial logging. So then again, the answer is, if we can get into these forests and thin them out, and in many ways sort of replicate the spacing of those old growth systems, then fires can hopefully operate in a similar manner to how they would have been in an old growth setting, and then produce higher amounts of charcoal. But again, what we're going to be talking about here is a form of biomimicry in that sense. We're trying to basically take what was a natural process and sort of enhance it to even produce higher amounts of charcoal. So this is one method, and this is called, we're gonna do the Lincoln log style in a second, which is called a conservation burn. And this is a methodology that is very specifically designed for in-forest produced biochar. You're not going to come away with like a tidy, nice pile. I mean, you can rake it up, but it's really designed for mimicking a burn pile, extinguishing it, maximizing your charcoal output, and then basically raking it back in to the soil, or raking it to the nearest tree. There's some interesting research to show that it seems to increase the fire retardant nature of developed trees in terms of their bark structure, as well as it has significant growth rate increases with small diameter and sapling trees. So that first 10 years seems to have a very significant impact on both growth rate as well as mortality rates. So the one meta-analysis paper found an average of 41% growth rate increase in the first 10 years when biochar was added. So if you're doing like a replanting effort, if there's either understory shrubs that you're interested in, or there's new species that you're trying to introduce, biochar is a great way to be then doing a burn, planting it right there, and or kind of moving the material a little bit over and planting it in space. You basically just, especially if you're replanting, you're just working it into the planting hole. And one of the nice things is that earthworms actually will do a lot of the process of, there's numerous research projects that show that earthworms will work the biochar in over time, as well as just the freezing that occurs where, I talked about it holding 6 times its weight in water. Then when it freezes, it just breaks up into all these smaller particles, and then the rains basically kind of wash it and work it in. So you certainly can rake it in a bit, but you definitely don't need to be like tilling it or anything significant. The goal is minimal impact. So I live on Waldron Island, so not too far away, and a group of us got NRCS conservation stewardship grants, and they require us to do those in kilns. And kilns, flame cap kilns, definitely maximize the production of material to biochar. It's also seen as one of these great low-tech, low-cost methods that is really ideal for in-forest produced biochar. And we basically are using tanks very similar to that water tank that's there. We've been getting them from San Juan Propane, and basically just using their old tanks that are in need of being scrapped on the mainland, and they're just giving it to us for free. And so there's options for people here on San Juan to also be accessing those tanks. In essence, it costs them more to get the tanks off to the mainland than they get in value in return, so they're happy just to like give them away. And there's a
250 or 500 gallon propane tanks.
Yeah, so the method, so we've been doing different sizes. One of the ones that's been best for us in terms of just high ease of use is the vertical 120s. They're basically 3.5 wide and a little over 4 feet tall. And yeah, you just cut off the top. And there's a welder also on San Juan who is interested and willing to do modifications of those tanks day and easterly. So if you want his contact, I'm happy to give you his contact. And it's just a low-cost way to be getting some of these tanks. And it's if you get much larger than that, you're then needing equipment to be moving those around, or at least some sort of winch system that you're moving it. But the nice thing about those smaller tanks is you literally can just roll them by hand. They're quite easy and maneuverable. And what we've really found, it's really different when you have an excavator. The one that's on site here is actually one that Carson's crew uses, and it's basically a 10 by 10. And I actually don't know, I think maybe it's like 6 or 7 feet tall. But it's ideal for an excavator just to be able to grab a whole pile of logs and toss it in. And that certainly, there's a lot of advantages and efficiencies to that. And if you have an excavator on hand, that's a great way to go. But if you're doing hand work, the greatest inefficiency of doing biochar production in the woods is basically the moving of material. So if you have smaller kilns, moving a lot of kilns to the material rather than moving the material to the kilns is actually the most efficient way to go. So that's where a whole slew of myself and my neighbor who are doing this, we're running usually like 5 or 6 of those kilns at once, and you can go up from there. But yeah, usually running quite a number. Yeah, fire needs 3 things. It needs heat, it needs material, and it needs oxygen. And there's been a lot of different designs that you'll see on YouTube or whatever, T-LUDs and retorts, and all of them are quite great. But when we started playing around with this, I first started maybe 7 years ago, and you're starting to look at the amount of biomass that you're trying to process in a forest restoration setting. All of those methodologies just seem to sort of ridiculous. They're just quite finicky and like super labor intensive to get to construct them. And so then we stumbled across these flame cap kilns, which were first used in Australia, and now Kelpie Wilson down in Oregon, she lives in the Salem area, has really kind of blown these up, if you will. And the basic concept is that the walls of the tank are limiting oxygen to being accessed, and then the fire ring that's on top is consuming the oxygen that's trying to get below. So as you keep adding more material and keep walking the fire up, everything that's below is basically living under the fire is called a pyrolytic wall. It basically is living underneath that pyrolytic wall or underneath that fire zone. And it is pretty wild. If you get to the top of a burn, it can just be raging on top, but you can stick your hand down at the bottom of the kiln and it's, cool or halfway warm, but not going to scorch yourself. Be careful. But no, it's impressive how much that oxygen reduction piece of the flame cap really is working and successful. And so one of the key things one of the big advantages of that too is that you're able to process larger material. We're kind of maxing out a little bit of what the conservation burn is really best at. This is probably 3 to 4 inches in diameter at the peak of some of these logs, and that's definitely works with conservation burns. But if you go up past that to 6 and 8 inches in diameter, your efficiency is it's not even really worth doing. You spend so much energy just trying to get the material to coal stage that your efficiency is well below 10% in terms of conversion to charcoal. Whereas those, like a good flame cap kiln, your weight conversion of dry biomass to charcoal is somewhere around 33 to 35%, and if a well done conservation burn can be right in the 20 to 25% conversion. So it's not, again, as ideal, but in terms of the ease of production and sort of the lack of needing to bring a kiln in, it's certainly a lot better than an open burn. If I had one mission right now in life, it would be to convince people to never do an open burn ever again. Open burns are off-gassing all of the carbon that's in that pile. It also sterilizes the soil underneath it. It burns incredibly hot in a way that a forest fire would naturally never do, concentrating all of that material in one spot. So you're biologically sterilizing the soil. It creates a location for invasive weeds to then be coming in, those pioneer species that come into the most disturbed sites, things like thistles and Scotch broom and all the things that we're not that excited about. That's exactly what wants to come into those sterilized areas. So, but the biggest thing is that in essence there's a soil amendment that could be produced and then put back into the forest that's not currently being produced if you burn it as a slash pile. So this is basically just a slight tweak of the flash pile. So maybe we'll start in on the process. So so I mean, so the big thing with conservation burns is that you really need similar sized material, and in this situation, it's completely ideal for larger trees, just using all of the branch material. So like if you were to take down that cedar and limit on up, all of those branches, you could make 2 or 3 different piles of those limbs, and that would be completely ideal for this application. And in that situation, you're really not needing to be overly precise. You're just throwing a bunch of branches together. But the key is that you're wanting all of that material to reach the same stage of conversion to charcoal. You're trying to basically get it into that coal form, and then you're trying to put it out at that sort of max point of where it's starting to really break into these smaller chunks. And here, in this situation where we have a small diameter tree, again, 4 inches at max, at its thickest, you're sacrificing all of the limb material to basically get the rest of the material started. So, all these branches, they'll burn up to be able to get this stuff caught, but that's basically sort of the trade-off. But again, if you start putting in like stuff of a whole bunch of different sizes, then it just gets really difficult to know when do you put it out, because you have some stuff that's halfway burned and you have some stuff that's already at ash, and then you have some stuff that's in some sort of intermediate zone. And so that's the biggest thing with conservation burns, is how much you can organize your material and how much you can organize material by both size as well as species type, because obviously BTU ratings of different species types, they'll burn at different rates. So you can't really mix alder and Doug fir too well. You'll burn up all your alder before you get your Doug fir to convert. So in many ways, again, it's just about organization. So so in this situation, your center of your fire is really going to be your branches, and we chose to leave this in its raw form just to show you like a very likely scene of what you might see with a forest restoration project. So you're just going to have a bunch of your branches, and you can see like it is again mimicking a burn pile. And you have these two, especially with conservation burns, you have these sort of 2 major windows of time that's really ideal, which is in the fall, right after you've had a few significant rainstorms, so that your ground moisture is, somewhat well saturated, but the material hasn't gotten too soaked yet, so that, it's going to have surface moisture, but it's not going to have gotten really into the material too far, so you still have a lot of that. The center is really, in many ways, as dry as it was in the summertime. Or then in the springtime, where you've obviously had a lot of rains, and then you've gotten to a point where you might have had 2 weeks of sun. It's been able to dry off a lot of that surface moisture, and in some ways dry out more of the center, but you're not really concerned about starting a forest fire because, again, high moisture content still in the ground. And so, that time period might be anywhere from late March through the middle to end of May, depending on upon the season. And then, at that end of May period is when you're starting to really push it. The flame cap kilns are safer to push even farther into the season. You can't legally do it when there's a burn ban, but because it's a contained fire, they're just quite a bit safer. You do really, with those, you want to you want to clear the space of any duff. So you want to clear down to mineral soil, just because it can catch duff and then have the fire spread through. So back to the conservation burn. We're just, we're doing a very basic limb pile. And again, this is sort of like the sacrificial material. I keep hitting my mic. And then you're going to start with your smallest diameter material, working your way up. And you're basically just doing it teepee style. So it's, a big version of how people make campfires. Yeah, this is probably not super exciting. You kind of already get the sense of what I'm doing. But then, you want it to be not overly finicky, but you are trying to standardize it as much as possible. So you're trying to make it symmetrical. You can make it like a little bit of an art project. Just again, because you're trying to maximize all of the material reaching the same stage of conversion at once. And so this fire with this size of material might be like a 30-minute burn or so. You might, depending upon the season, depending on how wet it is, that might change a little bit, but you'll start to see when it starts to break apart into chunks like 3 to 4 inches in diameter or so, or smaller. And you'll sort of see a bed of coals start to develop underneath the fire. And when you start to see that bed of coals, that's when to really think about putting it out. So again, one of the main things that you do need with this is some way to put out a fire. That one's a little long. And so water access is awfully helpful. If you do have a machine on board, you can use an excavator to put dirt on top of it and then kind of use the bucket to grind the dirt into the fire, and that can quench it. Many people don't have an excavator on site, so water's the the other great way to do it. I have done it in start the fire, put like a little bit of water, like when water was difficult, maybe I had like a 5-gallon bucket, but that was kind of it, and just do enough to get the active flames out, and then kind of just rake the material off to the side and just kind of rake it into the moist soil, and that also is mostly put out a lot of the coals. Again, if you have an area like it's kind of forest that surrounds somewhere near your house site that you can fill up buckets with a hose or something like that. It's really, again, pretty impressive that how little you really need to do to put on the fire to be able to get it quenched enough that you start raking it out and then starting to use some of the ground moisture. It really can be pretty minimal. But again, that is the big weakness of this form, is that you need some amount of water. Whereas the flame cap kilns, you also probably need at least a few gallons to be able to get some of the active flames out. But the difference there is that you're putting a cap on it at the end. Yeah, and that takes care of the oxygen. Exactly. So that form is really good for areas that you can't access water. When people hear about biochar, they oftentimes think about the terra preta soils down in the Amazon. I don't know if anybody has heard of terra preta here. Raise your hands if you have. Nope. All right, great. Which is an amazing story. It was there was a professor from Cornell, Johannes Lehmann, who published in 2003 a paper on these soils in the Amazon that had incredibly high rates of charcoal. It had basically 6 feet deep of just basically jet black soil, whereas all the areas around it had this light brown sandy soil. And the nutrient and biological activity was totally off the charts. I mean, Amazon, for as lush as it is because of the rainfall, it actually is super nutrient deficient because of that rainfall. It just has incredible leaching capacity of that soil. And but this soil didn't have that at all. It had incredibly high nutrient concentrations, and so they were doing research projects on why that was, and they were finding this charcoal that dated anywhere from almost 5,000 years ago to 2,500 years. So there was sort of like a pretty large window where charcoal was being added to those soils. And that was what they was attributing to all this high nutrient and nutrient count and fertility. But what's fascinating too is that in our area, and this is less known, like on Waldron Island, for example, there's an old camas garden that the Coast Salish people would burn in their camas garden areas, and there's different theories on sort of how they did that burning. But it also has this 3-foot deep section of jet black soil, and we did. That was the first year we did the University of Washington study. We were studying biochar's influence on 10 different farm sites in the county, and that camas garden had the highest nutrient retention properties of any of the soils that we tested that year. And basically nothing has been added to it for the last 60 years. So it's not for any sort of recent activity that it had such high nutrient retention capacities. That was all based off of its historic additions of charcoal. So it's just exciting that we have, in many ways, by doing this, we're sort of continuing a tradition that's been a part of this region for quite a long time. So you can kind of see where this is going. And so what'll happen is these will obviously just kind of, as the center burns out, this will just kind of fall in on itself. And especially it's important as you're like getting to these like last phases, like trying to kind of stick these ones up a little higher so that it falls in towards the center, because the worst is when you're getting like a little bit of charcoal in the center spot, but then you have all these sticks at the edges that are like halfway burned, and then you're kind of not really achieving your overall goal. So once you kind of have your basic structure, you're kind of trying to concentrate stuff so that it's going to fall in at that center point. But again, this is one of the reasons why I'm a big fan of more fires, smaller fires. It's the less you move material, the better. That's again going to be your biggest waste of labor is moving your material. Already moving down to that location is where I'm like spending most of my time just going and getting this stuff. So I think it's really like don't be afraid of small piles. It's they're super manageable and easy. So yeah, again, like we at any given time, sometimes we'll have like on Waldron and some of these projects for forest restoration projects we've been doing, we've had up to 12 or 14, somewhere in that range going at once. But yeah, one of the big things also is, I mean, you can do this. It's a little bit not the case if it's with branches, but basically, you're like, a burn pile, you're sort of like tossing stuff on as you go, and it's just kind of like you're just trying to move material. These, you're basically setting them up and you're torching it, and then you're not touching it again until you put it out. In some ways, charcoal and ash have a really nice synergistic process, because charcoal has the high nutrient retention properties, also known as cation exchange capacity, and then charcoal and ash have high calcium, magnesium, potassium, and then other trace minerals. And so you can throw off soil's base saturation, which is basically a little introduction into soil science. So there's these two categories called base saturation and cation exchange capacity, and basically cation exchange capacity talks about how many exchange sites are on a soil particle to be able to absorb and connect with different types of minerals. And then the base saturation basically says how much of those sites are actually open, because they can get clogged up with things like hydrogen, specifically hydrogen, because hydrogen is the most abundant element in the universe, but it has very little benefit for plants to be able to grow. So you can think about it like a parking lot, right? Like the cation exchange capacity is like how big is the parking lot, and then the base saturation is like how many of those parking lot spots are open. And so charcoal has a lot of cation exchange capacity. It just has a lot of these exchange sites. So even in sandy soils, it's providing a bunch of those nutrient holding capacity that is not naturally going to be in sandy soils. But then, so the base saturation piece, calcium, magnesium are the two biggest. They're considered of the macronutrients. They're considered sort of these gateway nutrients. Like if your base saturation levels are right, it's one of the reasons why people put lime or calcium on their ag soils, is to basically open up those. The calcium is one of the few things in magnesium, but more calcium, that dislodges those hydrogen molecules and separates them, and then leaves those sites open for other nutrients to get absorbed. And so it's a really essential thing to have in your soils. And again, ash has a high amount of it, so it's really beneficial. But if you have too much of it, then you throw your base saturation off. You start clogging everything up. So it can go on the other side. So anyways, the point is, some ash is really, really great, and as long as you're not building like, a real a straight film of ash on your soil, you're going to be pretty good. There's a lot of research to show that that 7 to 10 year carbon half-life that I was talking about, if you just leave the wood and it starts to decay, what happens? That charcoal will bond with, again, a lot of that labile carbon and slow those respiration rates. It's called the negative priming effect. In ag soils, it's become quite a big area of research. They've been finding some studies show a 69% reduction of soil respiration when biochar is added. So that means that it's, in essence, stabilizing the organic carbon that's already in the soil. So that's really significant. So if you have a nurse log that you're wanting to have move that direction, you also can just rake up some of the charcoal kind of right up to it, and it won't be an immediate sort of thing, but in time, as it starts to decay and starts to crumble over the charcoal, they'll start to marry and work together.